Let's record right away. Boom. Good morning again, folks. Welcome to Calc. So today's question is, what is continuity? We spent time talking about that last year. We're going to spend more time talking about it. So today we're learning to determine continuity. We'll be successful when we determine if a function is continuous on an open interval. So a couple things to look at. What is the limit of the square root of x at 0? So the question is, what is the limit right there? Well, in order to start thinking about that and have an idea, let's look at what's happening on either side. As we approach 0 from the right, so as we go down along this way, if this is little Benny or Bert the bug going down this way, they think they're approaching 0. What about if we try to approach it from the left? Well, we can't. Okay, sounds good, Savannah. So from the right, we get 0. From the left, we have nothing. So if the right is 0 and the left is nothing, the limit doesn't exist at 0. So that's one of the things we talked about previously, that the left and the right hand limit have to exist for the limit to exist. Good morning, Hannah. And there's Chris. So that's something I want to point out. So we're going to keep that in mind as we're thinking about what is continuity. We kind of briefly talked about left and right hand limits in an earlier lesson, but again, we're coming back to it again because I keep changing all the things all the time. Again, here's like breaking it down a little bit about why it's a negative, why there's a minus sign and a plus sign. Because the minus, again, it's coming from the left. Again, think of it's a little less than C, some number a little less than C. If you're a number less than C, what number does it look like it's approaching? Or if the right-hand limit is a plus, it's a little more than C. So what value are you approaching if you're starting at a number a little more than C and getting a little less more and more? But this bottom point down here is really the big thing that we want today. If both exist and agree, the limit exists. So it's something to keep in mind. And we're going to need that today. So what does it mean to be continuous? Well, our intuitive definition that we looked at in chapter 1 in pre-calc was literally just, I can draw a graph without lifting my pencil. That's our intuitive notion of continuity. But we need a little bit more. We can't just say, like on the AP test, they say, show it's continuous. You can't be, look at my doodle, yay! They're not going to accept that. It's great, it's good, it helps you understand what continuity is, but we need to go a little bit further. We need to have criteria to check. We actually looked at the formal definition of continuity in chapter 7 last year, and we're coming back to it now. And this is the same definition in this book as it was in the pre-calc book. So a function is continuous at a point, x equals c, if f of c exists, the limit as x approaches c exists, and the limit equals the function. If you think about sine, cosine, any polynomial, those are all continuous functions. So this bottom thing right down here is, we kind of skimmed over a little bit last year, but it's really like probably the more important part. So this is how we know if it's continuous at a point. That's helpful in everything, but we really want to know what if it's continuous on an interval. Well, to see if it's continuous on an interval, it needs to be continuous at every point on that interval. See? If all three conditions listed above are satisfied for all values of x in a given interval, then the function is continuous on that interval. A note on that, we always talk about things are continuous on open intervals. They're not continuous on closed intervals because we just looked at the square root of x. Square root of x was not continuous at x equals 0, even though the function existed there, because the left-hand limit didn't exist. If we said the open interval from 0 to infinity, it would be continuous on the into everything. So we're not including 0, but we're including everything up to it. Because if I include everything up to, but not including 0, I can still start to the left of that point because we're not including 0. I could start at 0 and see what value I'm going towards. So this is how we check to see if something's continuous at a point, or for that matter, on an interval. But functions aren't continuous sometimes. There's two broad types of discontinuities, and there's 3 total kinds of discontinuities from this. We have removable and non-removable discontinuities. And you kind of already know these a little bit. Removable discontinuities are holes. When you plug in a number and get 0 over 0, you get that indeterminate form of 0 over 0. That is a hole. Almost always it's a hole. I should say it's almost always a hole. An exception to that would be like absolute value of x over x. That is not a hole. But a hole is something like for this rational expression here, how I was able to factor it out and get an equivalent expression everywhere except at x equals -2. And now I can figure out what the limit is because I've simplified it into I have a different expression that's exactly equivalent everywhere except at x equals -2. But holes you should be able to factor out. There should be a common factor in the numerator and denominator, which is why we call it removable, because we can remove the discontinuity by replacing it with an almost exact equivalent function. So there's 2 kinds of non-removable discontinuities. One's a vertical asymptote, and a good indicator that's a vertical asymptote by analytically looking at things is when you plug in the number and you get something that isn't 0, a non-zero divided by 0. Like this clearly has a vertical asymptote at 2, because if you plug in 2 to this, you get 1 over 0. So a non-zero divided by 0 almost always is a vertical asymptote. The other kind is a jump discontinuity. The big thing with that is that you note that the left and right-hand limits don't agree. Your jump discontinuities are almost always piecewise functions, but you might not know that. A lot of the time we'll just give you a graph or a piecewise function, but usually not both, or like the equation, but usually we won't give you both things. So you want to make sure you're checking both of those things as you're working on stuff. Think about analytically, graphically, numerically, kind of check all the things before you make a determination one way or the other. Oh, I mentioned this earlier, but I'm going to mention it again because it's worth noting again. Functions can also be not continuous on the edges of their domains, like square root of x at x equals 0. So while square root of x has a domain that includes 0 and everything above it, it's only continuous on the open interval from 0 to positive infinity. Again, the open interval means you don't include the endpoints. Closed means you do. So even for the domain of square root of x, if I was a doodle, the domain for square root of x would be a closed bracket, 0, comma, infinity, open, parenthesis. Because infinity is not a number. You can't include infinity. You can approach it, but you never really get there. Infinity are always, whenever you're talking about a domain, it's always open brackets. But if you want to include the point, that's when you do the square bracket. Okay? And clear. Boom. A couple fun facts about continuity just in general. Like continuity is one of the huge parts of calculus, and it's something we're going to continually think about, especially that formal definition. If does a function exist, the limit exists, and do they both agree? We need to check it on our interval. And again, we do that by checking it at points throughout that interval. You do not have to check an infinite number of points, but you should check all the interesting spots to see what's going on. Differentiability, which we're going to come back to later, implies continuity. So if you have a differentiable function, that means that it's also a continuous function. That means nothing to you right now, but we'll come back to it in chapter 2. I'm just pointing out right now because it's something that we use often on the AP test. Like they say, oh, it's a differentiable function. but they don't care about the differentiability part. They only care about the continuity part. They're checking to see if you know what that means. So we always look to see if a function is continuous. Again, most of the useful theorems and properties require functions to be continuous. If functions aren't continuous, a lot of our things just don't work. Here's a couple. So there's three, I call them value theorems, that we're going to look at. They'll we'll talk about or in the reading in chapters 2 and 3. There's the extreme value theorem, the intermediate value theorem, and the mean value theorem. These three only work when you have continuous functions. And the mean value theorem needs to be differentiable, but that's a different story. We'll get there later. And also for average value, when we get to that later, you need a continuous function for that to work. Yeah. So continuity is big. We use it for a lot of different things, and we'll be using it in some level throughout the rest of the course. That's what I have for you today. I don't have tons more talking. The big things, the weekly plan changed a little bit. I thought we were going to do another activity today, but the more I looked at the activity I've planned, it uses a lot of the stuff we are doing today and on Wednesday. So it didn't make sense to do that yet and cut the activity into just shards and do a whole lot extra effort for way less payout. So we're just kind of moving on, and then we'll come back and do some kind of multi-section activities later on. So check out the weekly plan so you can see what's going on. You need to be in AP Classroom by the end of the week. So we are almost done, so you can go and check in there. Yeah, 1.4, 1.5, I'm putting both assignments up there right now so that if you want to start looking at 1.5, you totally can. The slides for that are in Schoology in the Chapter 1 resources. Again, my slides for everything are in the different chapter resource folders. I will, when I update them, they'll automatically update up there too. So just kind of keep that in mind. If you ever want to know what's going on, I'm going to try to make sure I always post a weekly plan. I give you more than that, but we've already changed plans about 5 times since I started writing a monthly plan. So I'm not going to give you a monthly plan, just weekly. Any general questions you have before we wrap it all up for today? Okay. So again, I would take some time to go back through. If you need a too long didn't read or didn't pay attention, here's a short version of it if you go back to it. So there'll be a lot more memes as we keep going throughout the year. That's where I spend half to 3/4 of my time planning. And I need to get more up-to-date ones for some of the things. I'm going to save what I've done, but I'll change things. That's it. That's all I have for you today. So you can either stay on and ask some questions, or you're free to go.